జుట్టు బాగుందా? ఇది ఎలా? ఓకే, ఇదేనా?
దాంతో రాయండి సార్.
ఇదే?
అదైతే క్లియర్గా నీట్గా కొడుకండి.
తడిగుడ్డు పెడతా ఉంటానా?
పొడిగుడ్డే మరి తడిగుడ్డ అయితే మళ్ళీ అదంతా కంప్లీట్.
సరే అయితే ఏసీ తగ్గిస్తావా?
ఏసీ తగ్గా
తగ్గించవా?
సార్ మీరు చెప్పేటప్పుడు శ్రమ పట్టించా.
సరే అయితే ఓకే.
లైట్ ఉంది కదా.
సరే సరే. పుట్టయ్య, ఓ పుట్టయ్య, రికార్డ్ అవుతుందా?
స్టార్ట్ చేశాను సార్.
చేసావా? వెరీ గుడ్.
రికార్డ్ అవుతుంది.
గుడ్ గుడ్.
ఇప్పుడు ఇది మూవ్ అవుతుంది కదా.
సరే సరే అయితే ఓకే. Yeah. Good morning, students. This is Dr. K. Venkatrao, professor in the Department of Mechanical Engineering. I am going to teach you machining technology. So, this is machining technology. So we also call this one as, here we see the metal cutting. So cutting of metal we see in this subject. So in previous semester you have seen the manufacturing technology. So in the manufacturing technology you have seen different manufacturing process. First one is casting, you have seen. So in that casting, in green sand mold making and casting you have seen, and also the conventional and special casting techniques also you have seen, like shell molding, investment casting. Those things also you saw in that manufacturing technology. After that one you have seen the mechanical working process. So mechanical working process, in this mechanical working process you have two types. You have seen hot working process and cold working process. In these two you have different techniques like rolling, forging, extrusion, etc. So in addition to that one, in the mechanical working process you have another category that is okay, we can say another category that is sheet metal working process. So in the sheet metal working process you have seen different types of methods. So they are shearing process. Shearing is nothing but cutting process, bending process, and that is spinning process, etc. These kind of process you have seen in the sheet metal working process. After sheet metal working process you have seen the welding process. So in this welding process we have different types of welding process you have seen. So arc welding and gas welding and special welding process. You have seen soldering and brazing, etc. So these are the all these operations. So most of the things I mentioned here, in all these process you have seen the fabrication of components. And one more thing here you can see, including casting. Including casting, you have seen different types of methods to fabricate the component. So in all these process, there is no loss of material, and we can say less loss of material. So loss of material is less. So in the casting, if you see, so we know the where we prepared the mold. In the mold you have the cavity. The cavity made the cavity in the mold is made as for the final shape of the object. So in that mold, molten metal is poured. After solidification, we are getting the product. The excess material is removed. That excess material can be remelted, can be used. So that's why loss of material is less. So even in all these process, say this, all the mechanical working process. In this, all the mechanical working process also loss of material is very less. So this in this process also shearing, bending, spinning. So you have another process, drawing process also. In this process also loss of material is less. So we know the welding process. This is one kind of joining process. So here also you have the loss of material is very less. So that's why in the manufacturing technology, the operations, so that is the different types of methods which are used to fabricate the object where the loss of material is less. That's why all these things are grouped under the manufacturing technology. So in the old days we call this one as production technology. So in the old days when we were in the BTech, we call this one as production technology 1. This is production technology 1. This machining technology we call as production technology 2. After that names we are changing, but thing is content is same. Subject name we are changing as for new trends. The names we are changing, but the concepts and that concepts and syllabus, everything is same with some little modifications. So advanced things we included in that one. That's all. So in this production technology 1, all these process fabricate the component with less loss of material. So in the production we can say the first process is casting process. Casting process is the first process to make any component. Say for suppose if you have a pipe or if you have a circular bar, this one is a circular bar. Say the diameter of this one is say 20 mm. 20 mm is the diameter of this one. So length of this one say 10 meters. 10 meters. Yeah. So length of this one is 10 meters. So let us assume this is made with mild steel. Made with the mild steel is the metal. So this is mild steel bar. So mild steel bar having the 20 mm diameter, 10 meters length. To make this one first initially, so in that casting process, we get the ingot. So where the ingot size is 700 by 700 mm size, this ingot size. From this ingot size, so where its cross section is square cross section, so side length is side of that is 4 sides are equal, side is 700 mm. From the 700 mm to this steel bar we make through the rolling process. Through the rolling process, we make the 700 by 700 mm steel bar into the 20 mm diameter, 10 meters length. Length is not problem. If the length is more, we can cut. Okay, so like that, through the rolling process, this ingot is converted into a steel bar having 20 mm diameter. So rolling process. So finally, what we want to say, the first process in the manufacturing is casting process. That's why we are calling this one as primary shaping process. This one is the primary shaping process. See, after primary shaping process, you have next process. So this mechanical working process, sheet metal, welding process, and other things. So in all these things, so we have the casting, hot working process, cold working process, shearing, bending, drawing, spinning, arc welding, gas welding, special welding process, soldering and brazing. In this manufacturing technology, that is production technology 1, here the problem is surface quality. See this one, surface quality is less. So less surface quality. So the components which are made by the manufacturing technology process where the surface quality is less, that is why we are going for the machining process. So in the casting, if you see, machining allowances you provided. For what purpose machining, machining allowance is provided to improve its surface quality by the machining process. That is one thing. And another, see this one here, in the manufacturing technology, the first disadvantage from this one, if you see these disadvantages, first one is less surface quality. Less surface quality. And second one, if you see, complex shapes cannot be made. Complex shapes cannot be made. So such cases, to get complex shapes with required surface quality, we should go for machining. So machining. So most of the cases, okay, machining process is used to fabricate the components. That machining technology we are seeing in this semester, this is machining technology. So where the fabrication of components, so we will see the manufacturing of components through the machining process. So one example I will tell you, after that we enter into the subject. So first, let us see what is the machining. Okay, let me clean this board. Right. Yeah. Say, let us see the concept of machining or philosophy. Concept of the machining, let us see. Okay, now I have a this is one workpiece. Where the size of this one, if you see, this one, let us assume 50 mm. So length of this component, say 100 mm. Height of this component, say 50 mm. So like that. So width is 50, height is also 50, and length of the workpiece is also 50. I think it is not visible. Okay. Yeah. So where I want to reduce the thickness of this one, to, so this is 50 mm. Height of this one is 50 mm. This height I want to reduce to 48 mm. 48 mm. If it is the woodworking process, what we do generally, carpentry, we know, if it is wooden piece that is on the table wise, we fix that one. We take a jack plane. With the help of jack plane, we remove the material. That I will show here. So where this one is 3D, in 2D I am showing. So this is the workpiece, right? This one is workpiece. So where we have a jack plane, this one is a jack plane. So this is a tool where we have. So like this, we have one tool. All of you know this one. So so when this jack plane is moved in this direction, manually we hold this one. So this is wooden workpiece. If it is wooden workpiece, wooden work, this is rigidly held on the table. This one is jack plane. Using this jack plane, what we do, we move forward like that. In the forward stroke, we remove the material. So manually we apply the force. So this one is tool. So when it is moved in this direction, this material which we want to remove, it is moving in this way. We are seeing this one as chip. In the form of chip, the material is removed. So this is conventional, that is planing of wood. So as the wood is, so this one is wood workpiece. As the wood workpiece soft material, we followed this one. So and one more thing, if you see the tool, it is a metal piece. This is metal tool. This one is wood. To cut this one, we used the metal tool. Why used the metal tool? The metal tool, because this is harder than this one. To cut one material, we have to select the tool which is harder than this one, then only it is possible to cut this one. So with wood tool we cannot cut this one. That's why we took the metal tool to cut the wooden piece. So okay, wood is soft material, that's why manually we cut. For suppose if it is metal work, so what is to be done? Manually it is not possible. For suppose this is metal, say mild steel. So to cut the mild steel, we have to select the metal tool. This we are selecting as high speed steel. This high speed steel is a high carbon steel. High carbon steel, in addition to the chromium, tungsten, vanadium, molybdenum, it is very hard material. So which is high speed steel is used to cut the mild steel metal. So okay, we selected the suitable tool material. How to cut this one? So manually we cannot cut. Our force is not enough to cut this one. Our force is not enough to cut this one. That's why on the machines we are cutting this one. For this purpose, we have one machine tool called as shaper. So I will draw this figure and easily you can understand how to cut this one. Okay, see this one. Let me draw this one first within. Okay, I will draw this one first. So this one is base of the machine. Okay, this one is shaper machine. So far you didn't see. Okay, in the lab I will show this one. Okay, however, here itself I will explain in detail. You can understand what is this one. So this is a housing or column of the shaper. So this is housing. Housing means it is box type in construction. So we also call this one as column. So it is box type in construction. So like this we have, right? This is box type in construction. So on top surface of this one you have a ram. So how that ram? Okay, in details, however, in the second unit you will see. For your understanding purpose, so just I am putting this one. Okay, you see. So this is housing or column. So bottom one, it is a base, supports the total machine. On top surface of this one you have a ram. So like this we have one ram, RAM, ram. So ram, where we have on front face of the ram, here we have right. So here we have a tool head. So I will tell what is the tool head. So tool head means here this kind of tool can be fixed. So where we have a cutting tool, so this one is high speed steel cutting tool is fixed here. So wait. Here we have an hand wheel. Like this we have hand wheel. So by rotating this hand wheel, we can move the tool downwards. So to give the depth of cut. So 1 mm or 2 mm depth of cut. See this one. This is where we want to remove the 2 mm amount of material. See this one. This is 2 mm. Right. So this is RAM. So inside we have one slotted link, where we have one slotted link. See this one, this is pivoted here. Here we have a crank. This one is sliding block. When the crank is, this is connected to this one. When the crank is rotated, then what happens? This rotary motion is converted into auxiliary motion, and then so then the auxiliary motion is converted into reciprocatory motion. So it moves forward, backward, forward, backward. So like that we have. So here on the front face of this one, on the front face of column, you have one arrangement. This is called as cross rail. CRASS, cross rail, where we have on the cross rail you have the table. This is machine table. M by C, it's nothing but machine table. So on the machine table, workpiece is fixed. See this one in detail. I will draw. So here we have the tool. This is top surface of the table. On the table, workpiece is fixed. See this one. This one is workpiece. When the ram is moved in forward direction, this material was removed. So to give depth of cut, by rotating this hand wheel, so we can give the depth of cut, how much depth we have to give to remove the material. When it is moved in forward direction, this material is removed in the form of chip. So same how we machine on the carpentry, in the same way here also metals we cut. This one is table, this one is workpiece, so this one is tool, right? So this one is chip. Okay, see this portion. So this portion I am drawing again here. How I drawn, you see. Right, this part I am showing here, you see. This is the workpiece. See this one? This one is the tool. Some part of the tool only I put here. Say some part of the tool only I put here. This is called as tool. This is called as workpiece. This is called as chip. So now the work is moving in this direction, sorry, tool is moving in this direction. This material is removed in the form of chip. So this we are calling this as depth of cut. This we are calling as depth of cut. Now, so now let us see the elements of metal cutting. Elements of metal cutting, if you see, there are three elements in the metal cutting. One is workpiece and another one is cutting tool, and third one is the chip. So these are the three primary elements of machining or metal cutting. So what are those things? One is workpiece, cutting tool, and the chip. These three are the primary elements in the metal cutting. So here what is to be done? The workpiece is rigidly held on the table. Okay, this one is table. On the table, workpiece is rigidly held, as well as cutting tool is also rigidly held. This one is tool post. And then when the tool is moved against the workpiece, when the tool is moved against the workpiece, material is removed in the form of chip. This is the concept of metal cutting. These are the primary elements of the metal cutting. What are those things? Workpiece, cutting tool and chip. In the examination, what you have to write? First you have to draw this figure. These things you have to put this one. After that you have to write that one as shown in the figure. Workpiece is rigidly held on the table, as well as tool is also rigidly held in the tool post of the machine. When the tool is moved against the workpiece, unwanted material, this is material we want to remove, unwanted material is removed in the form of chip to get required shape and size. This is the concept of metal cutting. So here, okay, fine. What is things? Workpiece and tool to be rigidly held on the machine. Rigidly held on the machine. Different places. So workpiece is held on the table. Tool is held in the tool post which is connected to the ram. Okay. Condition 1. Okay. After that one, what I told, when the tool is moved, against the workpiece, material is removed in the form of chip. Okay, right. So here two functions. One is workpiece tool to be rigidly held on the machine. Okay, on the table, on the tool post. Tool post is at the end of the ram. That is condition number 1. Condition number 2. When the tool is moved against the workpiece, material is removed in the form of chip. What is that material? Unwanted material. So what material? This is unwanted material. So when the unwanted material is removed, so we will get the required shape and size. So here, what is the role of machine? So here we have to see M by C, machine. What is the role of the machine? So here the machine should be able to hold rigidly the workpiece as well as the tool, and it has to provide motion. That is, when the tool is moved, who will move? Manually it is not possible. Who will move the tool? The machine has to move. The machine has to move the tool. So when the tool is moved against the workpiece, material is removed. So this moved. So where we need a movement or motion. So this moved. So it is nothing but motion. So now I will call this one as a relative motion. A relative motion between the workpiece and the tool. What is this relative motion? So relative motion is nothing but, once again I will draw a figure. Okay, see this one. This is workpiece. Here we have a tool. This one is tool. This is workpiece. This one is tool. If you move the tool many times, there is no removal of the material. Whatever the number, whatever the force you use, there is no removal of the material unless you give the depth. So when you give the depth, then only it is possible to remove the material. Okay, relative motion means there must be a physical contact. Physical contact. Without physical contact, not possible to machine. So relative motion is to be provided. So where we have three types of relative motions. Three types of relative motions. First one, first relative motion. So there are three types of relative motions in the metal cutting. See, let us see what are those things. First one is workpiece is stationary. Workpiece is stationary and tool is moved. and tool is moved. That is what we have seen. Workpiece kept stationary, tool is moved. This is relative motion 1. So relative motion 2, if you see, work tool is stationary. Tool is stationary and the workpiece is moved. That is planing process. Okay, I show in this, that will come in the third unit. So where the tool is kept stationary, workpiece is moved. And another one, if you see, third relative motion, both in motion. Both in motion. What is that both in motion? Okay, you don't know. In the second unit it will come, turning machine. In the turning machine, okay, that one also I will show. So you see this one, this is the round workpiece. This one is a round workpiece. The round workpiece is rotated like that. If you use the cutting tool, this one is cutting tool. When the cutting tool is moved in this direction, the material is removed. See this one, this material will be removed. So where the workpiece in motion and tool is also in motion, that is what, both in motion. So like that we have the three motions. Three motions. Now using this one, what I am doing, I define the machine. What is the machine? What is the machine tool? That I will define now. You see how I will define. Okay, here we have a difference between machine and machine tool. First you should see the difference between machine and machine tool. So that I show here. So machine and machine tool. Machine and machine tool. If you see the machine, okay, forging machine, mechanical press we have. So where it produces the components, but we are calling that one is a machine. See this one, mechanical press. This is one example. Like that we have many things. Mechanical press. Using this mechanical press we can perform the forging, and we have the rolling also, roll mill. Roll mill is also a machine. So these are used to produce the components, but there is no removal of the material in these two cases. No removal of the material. Whereas if you see this, this machine is called as shaper, where if you see the shaper, so where the shaper removes the material to produce components. Components are produced by removing the material. So that's why this shaper is called as machine tool. See this one. All the machine tools are machines, but all the machines are not machine tools. In the machine tools, components are produced by removing the material. In the machine tools, components are, machine tool is a machine. Machine tool is a machine. It produces the components by removing the material. Now if we see these two, mechanical press or roll mills, if you see, roll mill, MILL, sorry. So roll mills and mechanical presses, if you see, they also produce the components, but the components are produced without removing the material. That's why we cannot call them as machine tools. They are only the machines. The machines which produce the components by removing the material called as machine tool. All the machine tools are machines, but all the machines are not machine tools. See this one is a machine tool. See here we have one support, and bottom also you have support with screw, right? See this one is a machine tool. Come machine. This machine is a machine tool because here components are made by the removing the material. Now let us see the definition of the machine. So definition of the machine tool. So here I will write, you see, definition of machine tool. So what the machine tool's role? Here I told you, rigidly holding the workpiece as well as the tool, and it has to provide either one of the relative motion. That is the role of machine tool. That's why I'm defining this one as machine tool is a power driven machine. See this one, this crank is rotated by the motor, power driven machine which holds power driven machine which holds the workpiece as well as tool rigidly and provides relative motion between the workpiece and tool. That is definition of the machine tool. So these two, it holds the, see this one, this is a machine tool, is a power driven machine. So motor drives the crank, power driven machine. So this rotary motion converted into auxiliary motion, that is converted into reciprocating motion. And if you give the depth of cut by rotating this one, tool is moved downwards, we give the depth of cut where a relative motion is provided. Before providing that one, the workpiece is rigidly held on the table, the tool is rigidly fixed to the tool post, tool head, we call this one as tool head. So the first condition was satisfied. Next one, when it is switched on, when the motor is switched on, so relative motion is provided between them and it removes the material. So that is about the definition of the machine tool. Now let us see what are the different types of machine tools used in the metal cutting. Right. Okay. Now let us see the types of machine tools. So first one, turning machine. Turning machine. All the machine tools are machine. That's why I'm writing as turning machine or turning machine tool. We can also call this one as turner lathe. Lathu. Also call this one as lathe. Turning machine, turner or lathe, whatever you call it. Next one is shaper. So what we have seen, that is called as shaper. We also call that one as shaping machine. Next one is planer or planing machine. Fourth one is slaughter. Fifth one, drilling machine. Drilling machine. Sixth one, boring machine. And the seventh one is milling machine, where we have different types of milling machines. Eighth one, eighth one is grinding machine, and etc. So you have super finishing operations also. Okay, super finishing operations, they are honing machine, lapping machine. Okay, they also okay. Lapping and honing machine. Honing machines. So like that we have different types of things. Okay, in this machining technology, you have 5 units. In the first unit, theory of metal cutting. Theory of metal cutting. Already we have seen some of the things. Next one, if we see machine tools. So lathe, turning machine, all these machine tools you will see. Second and third unit you will see the machine tools. In the after that one, so we have the unconventional machining techniques. Unconventional machining techniques. So where we have two types of machining techniques. Two types of machining techniques. They are, say this one, conventional machining and unconventional machining. So like that we have two types of machining. All the conventional machining can be done using these machines. So conventional machining are performed or carried out on all these machines. See, these are the different category. Unconventional machining. What is the difference between conventional and unconventional machining? If you say, in the conventional machining, this is conventional machining, where we have a physical contact. I already told, physical contact between the tool and the workpiece. See this one, here we have the physical contact. So that also we calling that one as relative motion. Through that one, material is removed. In the unconventional machining process, it is not like that. So these conventional machining techniques we have since long back, we are using centuries back. This was developed. So these unconventional machining techniques were developed during the Second World War. These unconventional machining techniques were developed during the Second World War. So to machine the super alloys. What are these super alloys? These super alloys are very hard. Super alloys are very hard. So starting of this class, I told you to cut one material, the cut material, the tool which you use to cut should be harder than the material which you want to cut. For suppose I told you, if it is mild steel, so if the workpiece is mild steel, where the tool we used, this one is high speed steel. So high speed steel is harder than this one, harder than the mild steel. So nowadays we have the cemented carbide or tungsten carbide which are used to cut this one. So cemented carbide, high speed steels which are very hard. To cut that one, that cemented carbide or high speed steel, they are very hard we are saying. If you want to cut that kind of material, so it is so difficult to cut that one. Such cases we are using the unconventional machining process. A simple example, one only within 2 lines I will tell. After that, however, we will see in the fourth and fifth units those things. So what is that unconventional machining? See this one. This one is a workpiece, is very hard material. See this one, this is super Li. I want to machine for suppose electrochemical machining process, ECM, electrochemical machining process, that is chemical reaction will takes place. See this one. Okay, if you feel difficult this one, another thing I will tell you, electric discharge machining, so you can understand easily. Electric discharge machining process, where this one is a tool, this is tool, this tool is connected to negative terminal of DC, and workpiece is connected to positive terminal of, the super Li is connected to positive terminal of DC. Power supply to this one we connected. So when the current is passed, so between this one dielectric fluid, so this is called as dielectric fluid. So if you use the dielectric fluid between these two, okay, we continuously circulate the dielectric fluid between the tool and workpiece. So what this will do, this is connected negative terminal, this releases electrons. Electrons are released there. These electrons will collide with the molecules of dielectric fluid. So the electrons strike with this molecules of dielectric fluid, and then they become positive ions and electrons. So these are the primary electrons. So these are the secondary electrons. So amount of electrons will be increased. These electrons strike the workpiece. This workpiece struck by the electrons, and the positive ions strike the tool. So striking of electrons is more. That is why the metal in the workpiece will be melted and evaporated. So like that machining will be done. So whatever the hardness of the super Li, so whatever the hardness of the super Li, we can machine. That is why we are calling this one as unconventional machining, because there is no physical contact between the tool and workpiece. So like that we have different types of unconventional machining process. All those things like this is electric discharge machining, electrochemical machining process, abrasive jet machining, ultrasonic machining, electron beam machining, plasma beam machining, laser beam machining, and electrochemical discharge machining. Different types of machining process where we see all those things in that fourth and fifth unit. So okay, in the first unit we have seen the different types of machine tools. I think all of you clear this one. So now we go to the that is mechanics of metal cutting. Okay, right. So let us see the mechanics of metal cutting. We also call this one as chip formation. We also call this one as chip formation. Okay, right. Okay, one example I will tell you. If you have a glass, say this one is a glass. If you throw a stone, one stone is thrown to the glass here. So common sense, everybody, we know that one. So the force is distributed like that. So cracks will take place. Cracks will be formed. If the glass is strong, like that, cracks we have. If the glass is weak, okay, first cracks will be formed. After that, it will be broken and fall down. So that is the basic principle of force distribution when the stone is thrown on a glass. Okay, now let us see. So in the metal cutting, what happens? We see. Same thing. Okay, right. This one is workpiece is rigidly held, right? So this amount of material I want to remove from the top surface. Where we have tool, this one is a cutting tool. When the cutting tool is moved against the workpiece by the ram, so force is applied in this direction. As I said before, the force is distributed in all the directions. Like that, in all the directions, force is distributed in this direction also. So see this one, direction 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now we come from 11 to, okay. So the force which is distributed in this direction is not enough to make anything. It cannot cut. It cannot make anything. So that's why no effect in the workpiece material. Even this force is also not enough to cut the metal in this direction. This is also not enough to cut in this direction. This also not enough because of thickness is more. Workpiece is very strong, harder in this direction. That's why not possible. This force is not enough to cut this one. This force is also not enough to cut. This force is also not enough to cut. This force is also not enough to cut because see, material is more. The applied force is not enough. So in all these directions, it is not possible. If you see in this direction, okay, this material is sharp. In this direction, the material will cut. So machining is nothing but metal cutting. What what you think that cutting is nothing but cutting just like a vegetables. It is not here. Generally, the cutting word is saying that cutting the soft vegetables like knife. It will not be happen here. Even in the wood also, where you have direct cutting. Okay, in that wood and cutting of vegetables in that like that, here machining is not possible. So how the machining takes place, let us see now. How the machining takes place in the metal cutting, let us see now, right? Okay, this one is the top surface of workpiece. So in details I am drawing. So this material we want to remove. So this is depth of cut. right where we have the tool. This is the cutting tool. So here I am not putting straight line. Why straight line is not put? We cut here. See this one here, we cut this one. That is why this irregular line shows that cutting. Okay, now this one is the tool. Like this we have the tool. The tool is moved in this direction. This is called as tool. This is the workpiece. So this one, okay, here it is not visible. So this one is depth of cut, right. So as I told here, in this direction the material is weak because of less material we have. That's why machining is done, right. So when the tool is moved into the workpiece, okay, now here I am writing, when the tool is moved in the workpiece, metal in front of the tool gets compressed and flows plastically along a plane. That plane is called as shear plane. Along a shear plane in the form of chip. Okay. First conditions are same. Workpiece tool rigidly held on this one. Machine tool is a power driven machine which holds the workpiece as well as tool rigidly and provides relative motion between the workpiece and tool to remove the material. So here what happens? So when the tool is moved into the workpiece, okay, metal in front of the tool gets compressed. This one here. So where this is weak zone. Here the metal gets compressed and flows plastically in this direction, in the form of chip. So like that the metal is getting compressed. So in this direction the material is getting compressed and flows plastically in the form of chip. Okay, that in detailed figure I will draw what happens. So you should thoroughly understand this one. So because these are the fundamental things of the metal cutting, you should know very well. So that is why I am taking much time and writing everything on this board. So you should learn. You must learn it as a mechanical engineering. As a mechanical engineer, you are going to design and fabricate the components. You must know this one. Right. So this one is tool. Tool is moving like this. This is workpiece kept stationary. The chip is flowing like this. So this one is chip. So here when the tool is moved into the workpiece, metal in front of the tool gets compressed. So in this direction, Okay, enlarged figure I show you to understand easily. Right. So in this plane, this is the plane we are calling as shear plane. So here it is not direct machining. So what happens? Metal in front of the tool gets compressed and flows plastically. In this direction it is flowing. After that, in the form of chip, it is coming out. That is what the principle of this one. So that is why this plane is called as shear plane. What we are calling that one as a shear plane, PLN. This is a shear plane. So this one is chip, like that we have. See this one. This is the shear plane. We call this one as, let us assume, AO. So where AO is a shear plane. Shear plane. So angle of this one, see this one, this is pi. So pi is the shear angle. Pi is the shear angle. So this is the depth of cut. This one is chip is formed. So this is shear plane. Angle of the plane is called as shear plane. That is pi. So now actual machining, actual shearing. So shearing of metal will take place along the shear plane. If you see in details, shearing starts just before the shear plane and ends just after this one. See this one, this shearing starts just before the shear plane and ends just after the shear plane. So we call this one as PQRS. PQRS. So shearing starts at PQ, that is just before the shear plane, and ends at RS plane. RS, so just after the shear plane, at RS shearing ends. That's why PQRS is called as shear zone. PQRS is called as shear zone. So this is about the mechanics of metal cutting or chip formation. I think all of you understand this one. So later we see the types of chips. So how many types of chips? And one more thing you see, always the thickness of the chip. See this one? Thickness of the chip is equal to the length of the shear plane. Length of the shear plane. If it is T1, it is T2, thickness of the chip. So this one is depth of cut. So thickness of the chip is always equal to the length of the shear plane. That is why always T2 is greater than T1. T2 is always greater than T1. Thickness of the chip is equal to length of the shear plane. Almost, approximately almost same as that one. Right? So that is why this is chip formation. When the tool moved into the workpiece or entered into the workpiece, material in front of the tool gets, this is tool, this material in front of the tool gets compressed and flows plastically along the shear plane, and in this direction it is removed in the form of chip. Just like cutting of wood or vegetables, there is no cutting of metal here. That's all. Right. Now let us see the types of chips. Okay, let us see the types of chips. Okay, so in the metal cutting, there are three types of chips. They are continuous chips, and discontinuous chips, or we also call this one as segmental chips. So small pieces, not like continuous chips. Next one, continuous chips. Continuous chips with built up edge. We call this one as BUE, with a built up edge. So like that we have three types of chips. One is continuous chips, discontinuous or segmental chip, and continuous chip with a built up edge. So first let us see the continuous chips. Before seeing these things, we know that materials hardness is varying from one that is hardness of metal varies from one metal to another metal. Okay, I will take aluminum, copper, mild steel, medium carbon steel, and high carbon steel. Let us see. So by seeing itself, we can say cutting off this one is easy. It one also easy, not like this one. This one easy, but not like these two. And from here, this is medium carbon steel. These things will become hard, and cutting is difficult. Even in the cast iron also, branch, cast iron, these are the hard and difficult to cut. So these categories, they have good ductility, and before seeing this one, turning process also I will explain. Okay, turning later we see, not required. Okay, later we see the turning process. Okay, so now these are having good ductility. That is why machining is easy to machine. These are hard, machining is difficult, right? Based on material, we are getting the continuous, discontinuous, and the continuous chips with the built up edge. First thing, let us see the continuous chips where the conditions are. First conditions are, let us see, first condition, high cutting speeds. So high cutting speed, high cutting velocities. Next one is high rake angle. What is this rake angle? I will tell you. Third one is fine depth of cut. Fine depth of cut అంటే optimum or fine తక్కువ. And fourth one, optimum అంటే final. So we can say కావాల్సినంత, enough, that is as for requirement. This is optimum feed. So what are these rake angle, cutting speed, fine depth of cut, optimum feed? So to know this one, there is no way we should go to the turning process. I will tell the turning process, we see. So turning process is nothing but the turning process performed on the lathe. So where we machine the cylindrical workpieces. cylindrical workpiece. See this one. This is a cylindrical workpiece. So this is just like rectangle. This is just like rectangle. I am saying this one as cylindrical workpiece. So if you draw an axis at the center, so we can say this is a cylindrical workpiece. If you don't have the axis at the center, it is a rectangle. So this one is a cylindrical workpiece, rigidly held on the machine as per the machine tool definition, right? Okay, this is rigidly held and rotated. So like this is rotated, and where we have a tool, this one is a cutting tool. See this one, like this we have a cutting tool. When the cutting tool is moved in this direction, see this up to here, if the tool comes, this material was removed. So where we have the tool at the end of the pass, tool has come up to here, right? Like this we have. Say moving the tool in this direction is called as feet. So this one is called as depth of cut. So this is the cylindrical workpiece. Say for suppose diameter of this one, let us assume 50 mm. So where the depth of cut is equal to 0.5 mm, if the depth of cut is 0.5 mm, what can be the diameter of this one? This will be the 49 mm. So this phi symbol represents diameter. So this is a linear dimension, not see this one for the depth of cut 0.5 mm. So this one is the diameter, that's why it is shown with pi. So when you give 0.5 mm depth of cut, okay, to know that one, okay, I try in another way. So how the turning you have. Yeah, say this one is workpiece, this one is tool. So workpiece is rotating like that towards you. The workpiece is rotating, right? Workpiece is rotating like that. When the tool is moved in this direction, this material from the top surface of the workpiece will be removed. This is called as surface turning. Material is removed from the surface. Then what happens? This amount, this 0.5 mm. So on its periphery 0.5 mm removed. That's why this 50 mm became 49 mm. I think all of you understand this one. So this one is, say for suppose, so diameter of 50 mm. This is rotating like this. This is rotating like this. So if you know the diameter and RPM, you know. So RPM of the workpiece rotation, for suppose this is 500 RPM, workpiece is rotating, and if you know the diameter of 50 mm, so pi d n by 1000, that is cutting speed can be estimated. Cutting speed can be estimated as pi d n by 1000. Pi you know, d is diameter, n is RPM of this one. You will get the meters per minute, the cutting speed. So cutting speed is estimated, and depth of cut, see this one 0.5 mm. This is the depth of cut. This one is the depth of cut, how much depth the tool is moved into the workpiece. So that is depth of cut, fine depth of cuts. And if you see optimum feed, see this one, moving the tool into the workpiece in the direction parallel to axis of the workpiece. The tool is moved in this direction. The direction is parallel to axis of the workpiece. This is called as feed. So we measure the feed per minute or feed per revolution of workpiece. So generally we measure in this direction feet per minute. For 1 minute, how much length the tool is moved. So how much length the workpiece material is removed from the workpiece. So that is called as feed. Now let us see the rake angle. What do you mean by the rake angle? So I will tell only the one angle. So already we have seen the cutting speed, feed and depth of cut. So rake angle, this is related to the tool. So okay. Right, again to see in details of this rake angle, we go to the shaping process, what we have seen before. Right, so like this we have the tool without any tool geometry, solid tool. So like that we have the tool. Now we want to remove the material. This material we want to remove. So this one is tool. జాగ్రత్తగా చూడండి. If you see this one separately like this in 3D, it appears like this. Even the workpiece also like this we have. Now we want to remove this material. So when the tool is coming like this, see this one, what happens? When the tool is at here, when the tool is at here, the tool entered into the workpiece. So material is removed like this. See this one, material is removed like this. Like this material is removed, flowing like this. Okay, I will tell you one example. If you see the canal means water canal, where the water is flowing in this direction. Say for suppose in this direction, towards right side, the water is flowing in this direction with high velocity. When I put my hand like this, exactly perpendicular to the flow of water, if I put my hand like this, so due to water force, my hand will be moved like this. To keep my hand straightly, I have to apply the more force. That is common sense, you know. So for suppose, if I keep my hand instead of 90 degrees, if I kept some inclination, if I kept my hand like that, force of water on my hand will be reduced or not? Definitely reduced. So if you put your hand inclined to the flow of water, so what happens? Water is flowing like this and its water pressure on my hand will be reduced. If you kept straightly, what happens? It tries to shift the hand towards right side. If you keep inclination, so water flowing in this direction and pressure of water on hand will be reduced. So that is why the front face of the tool, what we did, we kept angle. So then what happens? So chip pressure So chip pressure on the tool is reduced and cutting forces also. Force required to cut the material is also reduced. See this one, like that the chip is flowing simply, chip pressure on that one is reduced. See this. This angle is called as alpha. This is rake angle. Rake angle is that one. And one more thing, this is the machined surface. The top surface of the machined surface is rubbed by the bottom one. This is called as, we are calling this one as face, FACE, front one. This one we are calling as flank, FLANK, flank. So what the flank is doing? Flank is moving over the machined surface. We need the machined surface somewhat smooth, quality surface. When the flank rubs the machined surface, then what happens? The rubbing marks we will see on that one. So even to remove the board, I am trying more. So because the writing marks are there. So this one is even simply with the pen to remove that marks. I am doing hard work. So this one is metal. So when the flank rubs over that one, the marks cannot be removed. So that's what is to be done. The flank you have to keep inclination. If you keep the flank inclined, then what happens? It prevents the rubbing of the flank with the machined surface. It provides clearance. That's why it is called as clearance angle. This is called as clearance angle. Okay, clearance angle effect on this one is less. So rake angle, if you have good rake angle, you will get the continuous chip. So we have seen what is the rake angle, right? So here the cutting speed, when the high cutting speeds used at high rake angle, fine depth of cut and optimum feeds, you will get the continuous chips. When these four conditions satisfied, you will get that one. In addition to these four, you have one more condition. It is possible only for ductile metals, not to all. Only in case of ductile metals, when you use high cutting speeds, high rake angle and high fine depth of cuts and optimum feeds, if you use, you will get the continuous chips. That is the condition for the continuous chips. So what are the other advantages? When the continuous chips are there, so it requires, so I told you, when the rake angle is used, what happens? So cutting forces are reduced. When the cutting forces are less, so power consumption is also less. Power consumption is also less. So for the continuous chips are, so how to write the continuous chips? Continuous chips are obtained in machining of ductile material when high cutting speeds, rake angle, fine depth of cut and optimum feeds are used. In addition to this one, fifth one, cutting fluids. So cutting fluids, in details of this cutting fluids we will see in this unit itself. So what the role of the cutting fluids here? They minimize the, okay, if you rub your hand, one hand over on that one, within 4 to 5 seconds you will see the heat generation due to friction. In the metal cutting, that is tool is moving on the workpiece. They are metals where the rubbing is very high. Rubbing is very high. Due to high rubbing of that one, high amount of heat will be generated. The heat affects the workpiece and tool properties. That's why if you use the cutting fluids, they absorb the heat during the machining process and it promotes the machining. So this is about the continuous chips. So continuous chips are formed in machining of ductile materials when the high cutting speeds, high rake angles with fine and optimum depth of cut and feeds are used. So in the ductile. So what are the advantages of this one? So good advantages with this one, if you say, so first one is good metal removal rate. Good metal removal rate. So where the chip pressure on the tool is reduced, so where the good tool life, and next one is good surface quality, good surface quality, and less power consumption, less power consumption. So these are the advantages with the continuous chips, continuous chips. Now the second case we see after the third case. So however we are seeing the continuous chips, that's why let us see the continuous chips with built up edge. So what is this one? Let us see. So we will see. So all the conditions, same working conditions. So same working conditions. What are the same working conditions? So high cutting speeds, high rake angle, fine depth of cut, optimum feed, and no cutting fluids. No cutting fluids. And one more thing is that one is no cutting fluids, and another one, this is continuous machining. Okay, even the cutting fluids are used. Even the cutting fluids are also used. We will see this built up edge. For our understanding purpose, I am telling you that there are no cutting fluids. It is a continuous machining process. For ductile metal, all the conditions we used except this one. What happens? Let us see. Okay. So tool where you use the clearance angle, rake angle is also used, and they see this one. So like that, chip is removed. Fine. Okay. So this one is a continuous machining process. So this is the chip and tool interface. When the chip is flowing in this direction, you have the rubbing over the tool face. So here heat will be generated in this region. Heat is generated. So this heat is divided into three parts. How the three parts? Three parts get divided. How it is dividing into three parts. Here there is no separation of the heat dividing like that. If it is 100 degrees, 30, not like that. Okay. This heat which is generated here, one part of it, that is some amount of heat absorbed by the chip. This one is chip, absorbed by chip and moving like that. So that will not affect the machining anything. So remain two parts. One part is absorbed by the tool and another part is absorbed by the workpiece. The heat is divided into three parts. One part is moved along with the chip, one part is absorbed by the tool, and another part is absorbed by the workpiece. So I told you this one is the continuous machining process. Continuously when the machining is going on, continuously heat is generated and accumulated in the tool as well as the workpiece. Accumulated in the tool as well as the workpiece. Then what happens? So when the temperature reaches to some amount, that is called as forge weld temperature. In the manufacturing technology, you have seen solid state welding. Okay, so when this metal reaches to some particular temperature, some amount of heat. So I show here some amount of workpiece material ఏం జరుగుతుందో చూద్దాం. Some amount of, see, I told you when the temperature in the workpiece reaches to a particular temperature, that particular temperature name is forge weld temperature, then some amount of workpiece material is welded on the tool face, sorry. So this is continuous process. Continuously this workpiece material is welded. So like that, welded over that one. So welded. So like that is growing. Size of this one is growing. So this is called as built up edge. This is called as built up edge. Now the chip is flowing over the built up edge. The chip is flowing over the built up edge. So then what happened? Chip pressure is acting on the built up edge. Chip pressure is acting on the built up edge. Then the built up edge will become hard. H-A-R-D, hard. Yala, how the built up edge become hard? So we know the work hardening. In the production technology you have seen. So in the forging operation, see this one, this is the workpiece. So when the force is applied on the workpiece, resistance forces will be developed against the applied hammer blows. So these are the resistance forces. These resistance forces are accumulated in this workpiece and it will become hard. If you apply the force, cracks will take place. This is called as work hardening or strain hardening. So due to this work hardening or strain hardening, then what happens? This built up edge will become very hard and became unstable. Unstable ante enti? They are not stable on that one. They are not stable on that one. They want to break. So when it became unstable, what happens? Due to chip pressure, this built up edge will be broken. So when it is broken, what happens? See this one separately I show here. This one is a tool. Like this we have the tool. This is the built up edge. Very hard. Due to chip pressure over that one, this built up edge is broken. When it is broken, this is welded one. Some amount of tool material will be taken out. This material will be taken out. There is loss of tool material. Now if you see the face, that is damaged. Tool face is damaged. When the tool face is damaged, its cutting ability is reduced. If you say the knife which is used to cut the vegetables, if you cut that one on the metal, what happens? Cutting edge is damaged. Its cutting ability will be reduced. Similarly here also, this built up edge, when it is moving away from that one, it takes some amount of tool material and it damages the tool face. Okay, best example I will tell you. So if you take the Fevikwik, that liquid we have, so generally we do experiments, the students and other thing. One drop if you place between these fingers, Fevikwik, and hold for some time and lift that. So these fingers will not be separated. Skin of either this finger or this finger will be separated, will cut. Similarly here also, when the material come out from the tool, so this tool face is damaged, its cutting ability is reduced. So further if you go to the machining, metal removal rate will be reduced, tool life is reduced, less surface quality and less power consumption. To avoid that one, what is to be done? So effective cutting fluids are to be used. If you use effective cutting fluids or coolants instead of cutting fluids, you say that one as if you use the better coolants. So what the coolants will do? They absorb the heat. What is the heat is generated? Absorb the heat and prevents the formation of built up beds on the tool. Right. మనం వేసింది చూసుకోవచ్చు ఒకసారి
అదంతా నాకు తెలియదు సార్, ఓన్లీ ఆఫ్టర్ స్టార్ట్ చేయటం ఆఫ్టర్.
సరే ఒకసారి నాగేశ్వరరావు గారు
సార్ ఒకసారి
ఓకే ఓకే సరే సరే
మనం కూడా వెళ్ళి చెప్పేసి వెళ్ళిపోతే
దీన్ని
అంటే